Okay, welcome to part 2 of trig identities, using trig identities, I guess we're called here. 2 more categories to go, even, odd identities, and then also the cofunction identities. These rely on understanding a little bit more. If you want to fully understand where these come from, there's actually an important definition to cover here. And then the cofunction one's actually based on primary trig, so that's not too bad. Super important. I shouldn't say super important. It can come up a little bit in the calculus. It's a property of what is known as an even function or an odd function. You know what even numbers are. You know what odd numbers are. It happens to be the case that there is a definition of a function if it is called an even function. Let's start right in the middle. A cosine graph looks like that. We've covered what the function looks like. We remembered it started at the top, and then it worked through one cycle and returned back to a maximum. Well, that's not actually the definition of even. That was just a review, right? So one cycle of cosine looked like that. The definition of an even function is symmetry in the y-axis. So here's your y-axis, okay? The cosine function, as you can see there, now that it's been pointed out to you, the cosine function is symmetrical about the y-axis. That is the definition of an even function. Okay, I'll make sure I put that into this. You might also have your own annotations. You don't, strictly speaking, have to know this definition to have a greater understanding of the identities, but it can help. Out of the 3 primary trig functions, there's only one that is even. Cosine is a so-called even function because it's symmetrical about the y-axis. Now, that is the graph definition, and it's certainly the easiest one, and that's why I started with it, to appreciate. But that has nothing to do, really, with this identity, where you're going to have to memorize that the cosine of negative u is actually the same as cosine u. What does that mean? Well, if you could first of all picture inputs and outputs once again. This letter u is the input. That's where an angle would go. And then we cosine the angle, and it turns into an output, right? Like we saw cosine of, say, 60 degrees. Cosine 60 degrees is a half, and a whole bunch of other ones. Obviously, I don't have them all memorized. If you put an angle in here, you get an output. Okay, so that's pretty easy. Input angle, output ratio. Well, so happens to be the case with cosine. When you put the exact negative of some angle, you get the same output. If you can try to think of both the left and the right side, of course, as outputs, okay? Because this is a function. Cos negative u actually is a function. And cos u is obviously a function. So what this is saying is if you take your input over here, which on the right side, it was just a positive u, and if you just straight away make it negative, so instead of putting in, say, 30 degrees, you put in negative 30 degrees, you actually get the same output. And we can see that visually on our picture. Okay, so take a look here. I'll just take this, whatever. Let's just say that's where u is. U is there. Okay, there's a positive. We're on the positive side, so there's the output. Okay, it doesn't have to be at a half, but it just so happens that I'm going to tick mark it right there. So maybe just so it's not that, let's say it's tick marked there. Right, that input where u is, maybe I'll make this permanent actually. So if the u is there, it's going to have an output, which is up there. If you go on the immediately left-hand side of the y-axis, then you're at negative u. Everybody knows that. And the outputs are the same. That's what that identity is saying. For any value of u, for any input, so like even if your u is way out here and you get this input output combo, right, on the symmetrically exactly opposite side of the y-axis, you're going to be down at the same output. That's what that identity is saying. It happens to be the case also for secant, because secant is just the reciprocal. Remember, we're just using division here, so we're taking all those y coordinates and we'll be flipping them over. Okay, you don't have to be able to explain this to a friend, but that is the context of the even identity, actually, because cos is even. This category gets called even odd because, like I said, only one of these is even and the other 2 are odd. This is the even identity of cosine. Where just exactly how you're going to use it algebraically, I'll tell you that later. But we also insert this here because even an odd function knowledge, that's not what all of calculus is about, but function knowledge is very important, in fact required in calculus. That's why we study it in pre-calculus. So some of these attributes, characteristics of functions come into play sometimes. It's not the vast majority of the time, but to know what an even function or an odd function is important. Okay, so that's the even one. My suggestion is that you memorize that cos is even, and then how it works. If you have the cos of negative something, or the secant of negative something, then that's just you're gonna feel like it turns it into a positive, but don't make no mistake, it's got nothing to do with factoring or multiplication or anything like that. It is this picture. That's what's going on, and hopefully that was understandable for you to understand. Sine's function graph looks like that. Quick segue, I just bolted away from it. You can tell that sine is not symmetrical in the y-axis, and it's not symmetrical in the x-axis either. Sine is actually symmetrical about the origin. And what happens here is, let's see here, for some value, let's see here, actually the easiest one to use is pi over 2. Let's say that's our input. We get the output positive 1. What happens in an odd function circumstance is if I make the negative input, so now I'm over here at the negative input, notice what I get is I get the exact negative output. That's an odd function, okay? For some negativization of the input, you also negativize the output. That's what that says in algebra, okay? If I negativize the input, because check it out over on this other side, if I'm positiving this input, so if that was my pi over 2, yeah, I would have to multiply that by negative 1 to make it equal to what's on the left-hand side. On the left-hand side, I've got the exact negative input. Okay, so in my example down here, my positive u was pi over 2. That lands me at 1, and you might go, I'm confused. Why is there a negative? Because you'd have to multiply by negative 1 in order to make equality happen with an input of negative pi over 2. Check it out, negative pi over 2, that output is negative 1. That is the odd identity. So this is odd, this is even, and this guy is also odd. There is also a circumstance, unlike with numbers, there's neither when it comes to functions. We didn't do a deep dive into functions and their even and oddness, and we're not going to. What you're going to be able to recognize is that in the trig functions, cos is even, sine and tan are odd. I didn't do a deep dive into tan. It's got the same aspect going on as the sine function, and the reason for that, they have y. They have the y coordinate in common, right? Sine revolves around y literally, and then tan also implicates y because it's y over x. Okay, and you can see that it has what's known as rotational symmetry. That's what an odd function has, is perfect rotational symmetry about the origin. I don't have space on this Jamboard slide to write those definitions. You might want to write those down, and I'll say them one more time. Symmetry in the y-axis is the definition of even. From an algebraic perspective, it means that if you put the negative of some input, then that's going to be exactly the same output as if you had done just the positive input. And then the odd algebraic definitions are a little trickier to say. I'll say it one more time in a second. We have rotational symmetry about the origin. That is an odd function. And then the algebra definition is, okay, if you're going to have some positive input, in order to get equality here, you're going to have to multiply negative of whatever y coordinate would have come out here if you're putting in the negative of your input. Okay? Now, once again, how are we going to use these in what context? Just one more thing, I'll say 10 more seconds about even and odd functions. You can do this with polynomials. We can classify square root function. You can classify all kinds of functions under even and odd. It just happens to be the case in our course. We're really only bringing it up with the trig functions, okay? And it's no big deal. How do we implicate these into problems? Well, that's coming up in just a second. Let me set that example up. Okay, here's an example. It comes from number 40 in our textbook. So that's what I've done here is to thread in some of the homework problem sections, but the even ones. So once again, it's recognize, remember, and then it's replace, and then just as a hint here, because we're really new at this process of what you're doing, it just says simplify. And what you're looking to do is, do you recognize anything? Do you see how you can replace anything? And then when you get to that next step, do you recognize any more? And then you're done. You should always have an x, a theta, or a u in your answer, by the way. Don't let those disappear. It's not technically correct to write the sine, the cosine, and stuff like that without x, theta, or u. Okay, and try to stay consistent with the question. So, recognize, remember. Now, it was just something I was just talking about, so we'll use it. You should be able to, because it was just on that last slide. be able to go, oh, I see something here. I see a negative input. So, okay, now hang on a second. Which one is it? Well, cotan is the reciprocal of tan. So I did reach a little bit here in this one. It's nice, kind of a nice one. Tan was odd. Okay, got it. So cotan's also got to be odd. Okay, what does that mean? What that means is you can replace out cotan of negative x with negative cotan x. Okay, your final answer in one of these problems is always got to be in terms of positive of the variable as well. We're not going to have an overwhelming amount of these even odd ones, so don't be too worried about it. But that's going to be, and that's going to be your clue that there's going to be an even and odd to be done, because you're going to see a negative input. And again, with this term simplify, what does that even mean? Simplify means make the simplest possible expression that we could evaluate if we had to do this without a calculator. So first and foremost, I've got to simplify using that even odd identity. So I get to the next line. Sorry, it all came up once there. I didn't anticipate that. Next of all, we have to do some more replacing, because we're not done here yet. We could spot that cotan is actually replaceable by cosine x over sine x. Okay. What you're going to grow to appreciate, I hope, is that there is a good revision of fractions in this unit, and we're going to deal with fractions a lot. And factoring is going to come up too. It's going to be great. Adding fractions, and all with actually with trig functions in them. So it's a great unit to test your skills and improve upon them. Anyway, let's finish the fun here. What you should recognize is there's a factor of sine x in the numerator and the denominator, and so it can be so-called canceled. I've divided the top and the bottom by sine x, and what that leaves me with is negative cosine x over 1, which should be written as negative cosine x. That's the final answer for that problem. And you might, fair enough, ask yourself, what did we really accomplish with that? And you might say, all you really accomplished was you got a simpler expression. I'm not even going to get into how you would have gotten this more complicated expression in the first place, because we don't have time. To wrap up this screencast, I'll just present to you what are known as the cofunction identities and give some background about where those come from. And then maybe one more simplifying. Okay, so just got a couple minutes, so better be quick. The cofunction identities are born out of this triangle. So we do finish with a nice primary trig example. If you have some angle u, okay, let's start there. Zoom it out. We have, from the perspective of angle u, you've got the opposite side, you've got the hypotenuse, and what's currently labeled there, the x, is the adjacent side, yeah? The cosine ratio of angle u is going to be this side right here. This is the cosine of u. Let me mark it in blue here. We're going to use this one, and we're going to divide by hypotenuse. Okay, that's cosine of u. Well, if you have some angle u, then you also have some other angle up in the top corner here, because remember you had 90 degrees. This guy up in the top is going to be pi over 2 minus u, or 90 minus u, right? So that's this angle up here. Well, if cosine of u was blue over hypotenuse, look at, that's the same as comparing from the perspective of pi over 2 minus u, that's the same as blue over hypotenuse as well. So that's why you have equivalence. That's the cofunction identity. So-called because it's a relationship between an angle and its complement. 90 minus an angle is called its complement. You know, complementary angles that add up to 90. Okay, and then there's the whole plethora of them there. How are you going to memorize those? I would say that, well, the co goes with, well, it's co. Cosine is in a complementary relationship with sine. And tan is in a complementary relationship with cotan. And secant is in a complementary relationship with cosecant. That's how you're going to memorize them. And let me set up one last example, and then we can finish this one off, okay? All right, we'll try to do this with a pause technique. There's the problem. The cotan of pi over 2 minus x times cosine x. How can you simplify that? I do have a couple of hints there. Give that a try. Okay, recognize, remember, it's come right on the heels of me introducing to you the cofunction identity. Again, like when you have the even odd, you're going to know that something's wrong here, and you're going to have to replace, because we need to simplify that down to positive, just x. So that turns into tan x for reasons that I've got on the side. And then you've got sine x over cosine x times cosine x, and that once again, cancels because of the whole common factor thing. Okay, that's the introduction of 23 new pieces of information and a couple of examples. I'll do part 3 with a few more examples. Thanks.